Dear professors, dear participants to the International Conference on Nonlinear Science and Complexity. First of all, I would like to thank to the organizers of this nice conference to give me the possibility to present my talk entitled Fractional Calculus in AI Theory and Application. I would like to introduce the journal Progress in Fractional Differentiation Application, and I kindly ask you to send your best related paper in there. As you know, fractional calculus deals with the study of so-called fractional order integral and derivative operators over real space domain and their application. Fractional calculus is a misnomer. Actually, integration and differentiation of arbitrary order is more appropriate. It was introduced in 1695, and we have 329 years of fractional calculus. Therefore, we cannot ask today what is a fractional derivative, because already since 329 years we know the content of fractional calculus, and this type of field is very powerful from both theory and applied viewpoint. The standard Riemann-Liouville left and right fractional integral are given here, and the corresponding Riemann-Liouville fractional derivatives are presented for order n. However, this derivative has a drawback. Derivative of a constant is not zero. In order to solve this problem, Michele Caputo discussed in this paper linear models of dissipation of squeeze almost frequency independent to the new derivative called Caputo derivative. This Caputo is 96 years old and still productive. Congratulations to him. And this is this famous left and right derivative, as we all know. And this paper, which started with the content related to experimental viewpoint and ended with the introduction, equation 5 of Caputo derivative. However, there are 4 origins of Caputo derivative as far as I know. First, initiated by Abel in 1822, he developed the fraction Caputo derivative of order 1/2. Liouville in 1832, he discussed and invented the Caputo derivative with the limit 0 infinity, and Zarbashan and Ercician in 1968 developed Caputo and generalized Caputo by using a pure mathematical approach. The whole motivation for studying the fractional calculus is the following: the standard mathematical models for integer order derivatives, including nonlinear models, do not work adequately in many cases where power law is clearly observed. Of course, we have to have in mind that the fractional calculus loses its standard geometrical physical interpretation. The index law is only valid when working on very specific function space. The derivative of the product of two functions and the chain rule have complicated expression. However, the fractional order differential equations, that is, those involving real or complex order derivatives, have assumed an important role in modeling anomalous dynamics or numerous processes related to complicated systems in the most diverse area of science and engineering. Some fractional calculus books, Orhan Espanie, some Coquil Malichev, Miller Herod, Baleanu Salut, Ilford, Kilbas, Krastava Trujillo, Megin, books of Maynard. Also the books of Parsha, Keji, Young Zhu, Bruce West, and many others authors during the last 20 years. Related to my co-author papers, I would like to stress on the fact that fractional calculus models and numerical methods has two editions, 2012 and 2016. Also, the second paper was published in 2015, and the papers with late Professor Machado and with Professor Albert Lowe, who is the main organizer of this conference, are listed here. I recommend the book Symmetries Analysis of Fractional Differential Equation, published in 2020 with Professor Hashemi. And also, I mentioned the books together with Singh and Kumar, Lopez, and book of Fractional Calculus Application, Agarwal, Yang Chen, and Ashad. As you know, fractional calculus has many applications. Here we have a fractional order controller of order 3 or 3.5 for a continuous dye laser used in high resolution molecular spectroscopy. After being used for a few years in Bordeaux, the experiment with the controller was sent to Colorado, and it was used by coincidentally was a Nobel Prize winner in physics in 1997. This fractional order controller was developed by Professor Gustavo, who was in fact the chief of Cron Group. By the way, a few months ago, we had a conference called ISFDA 2024 in Bordeaux, after 20 years of having the first event in Bordeaux 2004. Among the problems we have discussed in there, the most important part, according to me, was the roundtable applications of fractional calculus in industry. And the persons from industry came and showed clearly the application of fractional controller for antenna used by European Space Agency and the brake system used for cars, French cars, Citroën, Peugeot, etc. So we have plenty of application apart of them for fractional calculus. Since there are many fractional calculus operators, I would like to present here one paper, proportional fraction derivative, which is the combination of function plus derivative and used extensively by engineers. However, we have so-called fractional derivative with a singular kernel. This is the paper 2015, Caputo and Fabrizio, and they said this paper that they presented a new definition of fractional derivative as smooth kernel, in fact exponential kernel, which takes on two different representations for the temporal and spatial variable. The first works on the time variable, the third is suitable to use the Laplace transform. The interest for this new approach, the regular kernel, was born from the prospect that there is a class of non-local systems which have the ability to describe the material heterogeneity and the fluctuation of different scales, which cannot be well described by classical local theory or by fractional model with singular expansion. Since we are in China with this conference, I would like to present the relaxation diffusion model with non-singular kernels written by Professor Sun Hongwang and his colleagues and myself, where we present anomalous relaxation and diffusion process from the perspective of a new non-singular kernel. You know Mittag-Leffler function, its importance in mathematics, and it is called the queen of fractional calculus. The idea was to generalize the Caputo-Fabrizio, and how can we do? We use instead of exponential kernel, the Mittag-Leffler kernel, and we found the integral associated with this derivative, and it is presented in Formula 4. More details can be seen in a paper published in 2016. These fractional non-singular kernels idea was used successfully in mathematical biology and many other fields by several authors. Uh, Here I am presenting some applications together with Professor Armin, our colleagues. Here there is an anomaly equivalent electrical impedance response fractional operator with singular and non-singular current by Lenzi et al. But however, the fractional operators that we know, singular and non-singular, are particular cases of the ones developed by Boltzmann in 1874 and Sony in 1884. This is a more general kernel developed by Boltzmann in C. It contains many subcases. Another nice application of fractional calculus is Prag-Packard operator. If you think in terms of Prag-Packard calculus, we have the derivative in 5 and integral in 4. And this type of operator has the following property. We have singular and non-singular case together, depending on a parameter beta. So it is a non-singular operator in the case we have beta bigger than 1 and also in the case beta and 1. So it contains both. But however, if you like to investigate the more general kernel, you can find everything in this handbook of integral equations written by Baleanu and Mazurov in 2008. Here we have kernels, power law, exponential, hyperbolic functions, trigonometric function, inverse trigonometric function, elementary function, special function, kernel contain arbitrary function, and so on. However, we have a problem mentioned on the page 3 of this book for equation of the form integral from a to x of k of x and t, y of t, dt equals f of x, for x between a and b, where the function k x of t and f of x are continuous. If k a different from 0, then we must have f of a 0. So it is an extra condition on the data, which produces a serious effect when you try to initialize in terms of the non-singular operator in the Caputo type. So what can we do? We have to solve this issue. How it was solved? It was solved kernel by kernel. For example, for exponential kernel, for the paper presented in 2015, Caputo resolved the problem in 2021. And Losada and Newton resolved the problem in 2021 for the integral for the same operator. Well, this is the paper from 2021. So what is the idea? We start from integral from a to t in formula 2, and after we make step-by-step modification, we end up with formula 6. And in formula 6, as you can see, we have non-singular kernel, and there is no problem at origin. So we solve the problem for Caputo Fabrizio. However, there are other improvements for this Caputo Fabrizio operator, which were developed recently by Nieto et al. By Linear personified. For modified ABC operator, or operators with left kernel, in the paper RFI and Baleanu on extension of the operator meter-left kernel, we reported as an extension of fractional operator involving the meter-left kernel, which admits integrable singular kernel at origin. New solution of the related differential equation were reported together with some perspective on the modeling viewpoint. How did you do? We started from the mid-term left kernel, and this is the mid-term left kernel, and we integrated by part, and we obtain formula 5. So formula 5 contains a different kernel, which is singular, and we obtain an operator which can be initialized on L1 at origin. An interesting issue here for the mid-term kernel was that for the general case, for alpha between 0 and 1, MABC contains no derivative. So people ask, how can it be derivative of constant is 0? We prove it easily by Laplace transform. This is the case. But I want to give another example. Riemann Liouville contains derivative, rational derivative, but derivative of constant is not 0. So containing or not the derivative doesn't matter when you act on a constant system. What it matters is the structure of the operator. Here we have some applications to modify ABC given by different authors and with different purposes. And here we have maybe one of the nice definition modified version difference operator defined using Italian kernel, and this is the definition 18, 19, and this can be used in application for cancer and other biological applications. Also, we modify the mid-term kernel for the complex plane. And we give a geometrical interpretation of these operators. The suggested operators are investigated according to the concept in geometric function theory. Use the concept of convexity and star likeness. Therefore, they formulate a new operator in the Mamina class of analytic functions in order to act on normalized analytic functions. Our method is based on subordination, superordination, and majorization theory. And we give an application. This is 2, 3 to 4. These are the definition of Italian kernel. And I don't have time to give the details, but I want to the conclusion, especially the geometrical part. The geometric interpolation is a typical task in fractional calculus. As a result, the ABC fractional differential operator is studied geometrically in terms of a complex variable in this manner. This method reveals a variety of qualities and open the door for future generations to consider or change it in order to obtain additional geometric data. Geometric properties are illustrated, differential inequalities are formulated to include them. We explore that when F is convex, then IBR operator is also convex, while ABR operator is star-like. So what I would like to say that we give the right definition from a geometrical point of view of rational calculus operator in mid-term kernel. There, in my opinion, there are few or maybe none well-posed geometrical meaning of rational operator. For more information about numerical methods for both single and non-single operators, you can see the YouTube page of Sun Accuracy. Some new trends, according to me, is related to fractional Mayer neurons for intelligent computing software for nonlinear fractional intelligent systems. Another fractional operator application for neural networks using proportional capital derivative, generalized fractional differential equation for path dynamics, nonlinear higher order fractional terminal values problem, new fractional signals multi-integration with short memory and variable order. However, in the modeling approach where the AI and fractional calculus play a significant role, we have to take into account that there is no absolute model, and in fractional calculus particularly, we don't expect a single kernel or a single class of kernels to be able to be applied to all type of phenomena. So this is important to see the remark of Giovanni Galabotti in the Elements of Mechanics in 2007 about modeling. Also, it's better to use the 5-step method. Ask the question, identify the modeling, first, formulate the model, solve the model, answer the initial question. More details you can find in reference 1 or in the book to Mark late Professor Mark Mesh. Also, you can use modification of Erdős fractional derivative in your studies if you wish. Applications of fractional calculus in mathematical biology can be done very easily and successfully, and this is the motivation and prediction capability of proposed model for classical and fractional. Comparing the fractional is better but not ideal, of course, as you can see from this data. Also, we have some papers published here, together with Professor Janjarny, on fractional modeling and optimal control. Another one by using the appropriate dimensionality of fractional model explained in this paper. Another paper is a new comparative study on the general fractional model of COVID-19 with isolation quarantine effect. Another one is Professor Nieto on COVID, a general fractional formulation tracking control of immunogenic tumor dynamics. Another one is a new and general fractional arranging approach, a faster microphone case study. Then a new and general fractional arranging approach, a faster microphone. On the fractional optimal control problem with a general derivative operator presented in the formula 11, 12, 13, 14. And on a new and generalized fractional model for a real cholera outbreak. And some now things about artificial intelligence and fractional calculus. You know, artificial intelligence is not a new topic. It's fundamental nowadays, crucial for the humanity, with huge application and huge trend, and everything was given here. But the concepts are not new, and also for the same deep learning evolution. Fractional calculus was combined with wavelet, combined with fuzzy, combined with delay, combined with many other concepts. Now the combination is artificial intelligence. So here I am trying to summarize few applications with the impact or real world impact. Neural network models in biology. Fractional calculus enhances neural network model used to simulate neural activity and brain function, accounting for the complex temporal dependencies present in biological neural networks. Image processing in computer vision. Fractional calculus can be used to enhance edge detection algorithms, allowing for more precise identification of edges in images by capturing fine details and reducing noise. Modeling biological systems. Fractional calculus used to model complex biological systems that exhibit memory effects and non-local interaction, providing more accurate simulation of biological processes. But however, some applications can be done in fractional variation principles, and the AI applications were presented by Professor Yan Quanchen in Bordeaux. Here I would like to remind an article from 2008 in Science Watch when they discussed about how Hamiltonian, partial Hamiltonian formulation, and these are the equations containing left and right derivative, unique in mathematics, and with many applications in vibration and control. For example, we have some old papers, important papers for Lagrangian formation of classical field, Lagrangian linear velocities, rational Hamiltonian and also combination delay, some concrete solutions of some Lagrange equation, and a nice application, medical study for fractional Lagrange equation of harmonic oscillator on a moving platform. Here we have a term which is non-zero and alpha is between 0 and 1, and when the term disappears, is the term from formula 1, 11, and this term disappears when alpha goes 1. So this type of system can be treated with the help of AI and fractional calculus. Also, fractional optimal control, you can see an old paper published in 2007 and papers published later related to optimal control. In nuclear magnetic resonance, there is a huge applications, and this the first paper published in 2008 is the main and the first one in the field. Now there are plenty, and you see how we treat the description of NMR by the importance diffusion in medicine, how you formulate the classical block-Torah equation, and then how to introduce in 2008 the correct dimension fractional block-Torah, and how you prove that this equation gives better result than the fractal model. So I would like to thank you very much for your attention.